Okay, now in order to understand or apply the concept that we developed about discrete time Fourier series, let's consider some examples related to discrete time Fourier series. So let's assume we have a signal x of n equal to sine omega naught n. Now we already know that this signal may or may not be periodic. And the condition that this signal must satisfy is, let's consider the first case. This signal will be periodic if 2 pi by omega naught is an integer. So 2 pi by omega naught. If it is equal to integer, then this signal will be periodic. So from this equation, we can see that omega naught comes out to be equal to 2 pi by capital N, and this capital N is the fundamental period. Now, how to represent this signal in the representation that we derive? So what is the Fourier series representation of any discrete time signal? These are two equations. Now, in order to represent this signal in this particular representation, we need to find out Fourier coefficients. But this signal is a quite simple signal. We can make use of Euler's relationship, and we can directly represent this signal in this form. And then by comparing this particular representation with this, it's obvious that whatever is the value of k, so whatever is the value of k, that is going to be the coefficient. So in this case, you can see the value of k is 1. So it means this thing, it must be equal to a1. Over here you have minus, so over here you have k equal to minus 1. As a result, this particular coefficient is a minus 1. So in this example, which is a very simple example, we don't need to make use of this particular equation to find ak. We can directly represent this in Euler's relationship, and then we can easily identify that this particular signal has two coefficients, a1 and a minus 1. But if you remember, there is a periodic nature associated with the Fourier coefficients of discrete time Fourier series. So let's consider a specific example. We haven't specified what is the value of n. So let's consider that the period of the signal is 5. Okay. So 2 pi by omega naught is equal to 5. Okay. So omega naught equal to 2 pi by 5. So if you plot this signal, so we have this one, if you can see these are the Fourier coefficients. So in this graph, we are actually plotting Fourier coefficients ak as a function of k. So we have a1. So you can see we have one straight line with a value equal to 1 over 2j. So this is a1. And then we have another coefficient which is k equal to minus 1. And you can see that this is minus 1 over 2j. So this is a minus 1. Now, the periodic nature of Fourier coefficients for discrete time case is ak is equal to ak plus. And now for this particular case, we are assuming that period is 5. This is 5. It means a1 must also be equal to a6. And you can clearly see this is a1. And then we have the repetition of this at k equal to 6. As well as this is this signal is going to repeat itself at a number of this value. So you can see that the general expression, if I further elaborate it, this can also be equal to ak plus r times n. R times n. So in the first case, I consider k r equal to 1. So as a result, for r equal to 1, and then putting k equal to 1, so you end up a1 must be equal to a1 plus 5, so it's 6. Also, a1 can also be equal to, now consider r equal to 2. So 2 multiplied by 5, 10. So a1 plus 10 is equal to a11. So this a1 will also repeat at 11. You can see you have another repetition of this, and then this thing is repeating. Similarly, you can see a minus 1. So a minus 1, when it will repeat itself. So based on this equation, a minus 1 will be equal to a minus 1 for r equal to 1. So we have minus 1 plus 5. So it becomes equal to minus 1 plus 5 becomes equal to 4. So you can see this signal is, this particular coefficient is repeating itself at 4. And then it is repeating at 9. Similarly, on the left hand side, you can also see that a minus 1 is also going to repeat itself at minus 6. So this is what I were talking about, the periodic, which is shown only by Fourier coefficients of discrete time Fourier series. Okay. Now let's consider another possibility. I mentioned that this particular signal sine omega naught n, it is periodic under two possibilities. One is if 2 pi by omega naught is equal to integer, and the second possibility is if 2 pi by omega naught is equal to ratio of integers. It is equal to ratio of integers, then we also can get, so it's also possible that 2 pi by omega naught is equal to n by m, where n is integer as well as capital M is integer. So in this case, omega naught will be equal to 2 pi by capital N into m, as mentioned over here. Now, once you have this particular representation, so now what will be x of n? X of n, if it is periodic, now we have omega naught can be represented by this thing. So how to represent this signal in terms of Fourier series? Again, rather than making use of the equation of ak, I can directly use Euler's relationship, and by making use of Euler's relationship, I get this. Now, what is the value? What is this coefficient? A 1 over 2j and minus 1 over 2j. Now, they are not a1 or a minus 1. You need to find out what is the value of k over here. And you can clearly see this is k and this is k. So it means this coefficient is for represented as a capital M, and this one is actually the coefficient at minus m, and that is minus 1 over 2j. Now let's consider a specific example. So let's assume that capital N is still 5, so it means period of the signal is 5, and this m is equal to 3. So as a result, it means that omega naught becomes equal to 2 pi divided by 5 into 3. 2 pi 3 by 5. Okay. So in this, it means that this m corresponds to now 3. So it means this coefficient is a3 and a minus, a3 and minus 3. So let's look at the graphical representation. You can see this is again the plot of Fourier coefficients for this example, when x of n is like this. This is k. So we have a3. So this 1 over 2j is a3. And then we have a minus 3, this one, which is a minus 3 is equal to minus 1. And then you can see the repetition of this particular coefficients, which is at 3. So a3, based on this equation, ak is equal to ak plus n. So 3 n is 5, so it means a8. So this coefficient is going to repeat itself at this position, and you can see. Okay. And then this is the periodic nature. You can easily identify this is repeating itself. Similarly, this particular coefficient is, again, this coefficient is also going to repeat itself on the negative side. So a3 will also appear at a minus 2, at a minus 7, And similarly, this particular coefficient a minus 3 is going to repeat at this place, at this place, and this place. Okay. Similarly, let's consider another example. So this is example number 2. So let's assume we have a signal given to us in this form, and you can see it is periodic based on the result that it involves sine function and cosine function. But this is not what we want. We want to represent this in the standard exponential form. So again, rather than making use of the expression of ak, I can directly represent this sine function in terms of exponential based on Euler's relationship. And then you can collect the terms together so that all of the terms related to this comes together. And now, if you look at this, now this is the representation of the given signal in terms of complex signal. But we need to find out what is this representing. In the general representation, you can see that this constant value corresponds to A naught. So A naught is equal to 1. What is this? This corresponds to, if you look, what is the value of K over here? K is equal to 1. So this means this thing must be A1. So A1 is 3 by 2. This is K is equal to minus 1. If you look at it, this is K equal to 2, and this is equal to K minus 2. So whatever is this thing, this must be representing A2. This must be representing A minus 2. And this is what is written over here. Okay? Because e raised to power j pi by 2 is e raised to power j pi by 2 is equal to j. So that is why it is j by 2. Okay? And e raised to power minus j pi by 2, if you solve it, is minus j. So that is why a minus 2 is equal to minus 2. Now, coming to the representation. So if you plot these coefficients on the plot, so this is the magnitude, because in this case, you can see that in this case, Fourier coefficients are complex. So whenever you have a complex number, let's say z, so you have its magnitude and you have its phase. So generally, Fourier coefficients are complex. So when they are complex, you need to have two graphs. You need to have two plots, one for the magnitude and one for the phase. So this is, you can see the magnitude of the Fourier coefficient, and this one is the phase of the Fourier coefficient. So this is, you can call it magnitude plot, and you can call this as phase plot. And now coming to this third example. This third example is related to a square wave. So this graph, you can call this signal as discrete time square wave. Discrete time square wave, because its shape is very similar to the continuous time square wave that we have covered when we were dealing with continuous time Fourier series. But now this is not this. In this case, it was continuous variable, but now this is a discrete variable. But its shape look like as if you have taken the samples of this signal. So it means as if you have samples like this. Okay. So this is a periodic signal. Its period is n. Now, in this case, we cannot use Euler's relationship. We have to find out. So if I want to, so this is x of n given to you, and you are asked to find out its Fourier series. So what is the Fourier series of this signal? You have to now, in order to expand this, you must know AK. So what is all we need to do is find out AK. So AK can be find, you can use this equation, which we have derived already. This is the expression x of n raised to power minus j k 2 pi by capital N to n. So all we need to do is we have to sum this signal over period n. Again, you can see that this summation is over n number of values. It doesn't matter from where we start. So you may start from 0 to n. So this is one period, but it is better because this signal is symmetric with respect to 0. So normally we consider, we take that interval which involves this whole interval. So maybe somewhere over here you have minus n by 2, and somewhere here you have plus n by 2. So you can integrate, or sorry, you can sum this within this interval. And because this signal is 0, it is only non-zero between minus n1 to plus 1. As a result, you can see in the summation, we only need to sum from minus n1 to plus 1. And within this interval, the signal value is 1. So you end up with this signal is equal to 1. And then you have this expression, which is right. Now, all I need to do is to find out what is the result of this. So whenever you have something like this, it is better to transform it with the change of variable. What you need to do is we can replace. So in this case, our variable is small n. So what we can do is we can introduce another variable small m, which is equal to n plus n1. Okay. If you use this, then what will happen? What is the advantage of this? That your summation, the lower limit becomes equal to 0, right? You can see an upper limit, it doesn't matter what is the value. And whenever you have this type of result, you can always use a geometric series, which I'm not going into detail, but you can easily find out that if you have something like this. So what is the general result I'm asking you to look at? That if you have x raised to the power n, let's say x raised to the power m, such that m is from 0 to capital N. Okay. What is the result? What is this summation end up? It ends up into 1 minus x capital N plus 1 divided by 1 minus x. So this is the result that now you can use over here. So this is, you can see that this is x. I am representing this by x, but of course, in our case, x is corresponding to this exponential signal. So this is all mathematical manipulation. There is no signal system concept involved. All you need to do is simplify this expression, and ultimately you will get your result like this. So this is Fourier coefficient. Now, there are two possibilities. If k is not equal to 0, minus plus n, minus plus 2n, then Fourier coefficients will be equal to this. But when k is equal to 0, minus plus n, minus plus 2n, then Fourier coefficients will be equal to this. Okay. Now, just to give you the visual representation, how these coefficients will look like. So one specific example is, let's consider that we have a signal for which 2n plus 1 is equal to 5. And then we can consider three possibilities. For in first case, we assume that period is equal to 10, then second case period is equal to 20, and then third case period is equal to 40. So what we are doing is, in this signal, we are changing this period, but we are fixing this. So minus n plus 2n, so 2n1 plus 1 is equal to 5. Okay. So if you plot this, this is what you will get. So this is for n equal to 10. This second one is for n equal to 20, and this third one is for n equal to 40. And you can see the difference in the behavior of the Fourier coefficient. So in this case, because Fourier coefficient is a real number, so we only end up with the magnitude plot. So you can see what is actually happening as you increase the period of the periodic signal. The Fourier coefficients, they are getting closer to one another. They are getting closer to one another, okay? Because these coefficients, if you remember, what is actually happening along x-axis, we have k. So actually, when you increase the period of the signal, so frequency of the signal will reduce. So time period is increasing, so it means fundamental frequency will reduce. So it means lower frequencies components will get, they will have more pronounced effect. Okay. So then, rather than I talk about in detail the properties of discrete time Fourier series, because the properties followed by discrete time Fourier series is exactly similar to the properties that are satisfied by continuous time Fourier series. And in today's lecture, I have explained, I have derived the properties in detail. So I'm not going to derive the properties. I'm just going to tell you that the discrete time Fourier series also satisfy all of these properties mentioned over here. So as an example, if I talk about one property, linearity. So what is the meaning of linearity property? It means that if you have two signals, let's assume you have x of n, and its Fourier's pair is, let's say, ak. There is another signal, y of n, and its Fourier series pair is bk. Now, if you take a linear combination of these two signals, so let's say a times x of n plus b times y of n. So now you have taken a linear combination of the two signals. So according to the linearity property, what is going to be the Fourier coefficients of this new signal? So again, just for notation purposes, I can call this signal as z of n, and I can say that this new signal, its Fourier coefficients will be, let's say, ck. Now, what is ck? Ck will also be equal to the linear combination of the Fourier coefficient. So a times ak plus b times. If you remember, I proved this property for continuous time, and I'm not going to prove it. You can, I will synthesize, I will advise yet that you practice all of these properties. So if you have this signal, so this is the corresponding Fourier series. Again, we have time shifting property. If x of n has Fourier coefficient a of k, so what will happen if you time shift the signal x of n minus n naught? So what will happen? Fourier coefficients ak will get multiplied with e power minus jk 2 pi by n into n naught. So how much time you introduce, this factor is going to decide. And then conjugation property, time reversal property. So the one difference that I will emphasize over here is, in the case of discrete time, we don't have derivative, we have difference. So in place of first derivative, we have first difference. First difference means x of n minus x of n minus 1. So what is going to be the Fourier coefficients for this signal? So x of n Fourier coefficients are ak minus, what are the Fourier coefficient of x of n minus 1? Now x of n minus 1 correspond to time shifting operation, and we already know time shifting has this effect. So what will be the Fourier coefficient? It will be ak e raised to power minus jk 2 pi by n, and in this case n naught is equal to 1. So we have 1 over here, and then I can take ak as common. So ak and 1 minus e power minus jk 2 pi by capital N, which is exactly this one. Okay, so that is something that you need to consider, and it's important that you go through these and then try to derive all of these properties, including this Parseval's relationship. So this one is the average power. If we are given this signal, and if we are given information about signal in terms of its Fourier coefficient, and then we want to find its average power, then you can make use of this result. And according to Parseval, they are equal. So that's it for today's lecture. See you next time. Allah.